Hi guys, welcome back to my channel Programming with Pirai. In this video, we are going to see about Leetcode question number 21. Merge two sorted list. You are given the heads of two sorted linked lists and they are list 1 and list 2. You have to merge them and return a single linked list which have a sorted order of list 1 and list 2 combined. Okay. Now let us see the example so that it will be more clear. See here. So this is the example. So it is a input. If they have given this as our input, then our output should be looks like 1, then 2, then 3, then also 3, then 4, then 10. So this should be our output. Can you understand this? Now, how to approach this problem? They asked us to just return this combination of two linked list in a sort order. That's it, right? So I have an idea like store all the node in a array. In an array. Okay. After storing it, just sort it. Just sort it. You know how to traverse, right? Just traverse from 1, 3, 4, 10, put into the array. 1, 2, 3, put into the array. Now it's time to sort it, right? Then reconstruct a new linked list. Reconstruct a new linked list. So this is my first approach, right? Brute force approach. What is our time complexity? I can say time complexity is O of n and plus m. Sorry. If you take for example this length n and this is the length m, then it is O of n plus m. And what is my space complexity? It is also O of n plus m because we are first storing into an array, then also we are storing into a linked list. So this is our first approach. Okay, can we optimize it? Fine. Let us think about it. Just see here. I can say in here it is sorted and it is also sorted. So if I use two pointer and check whether which is the smallest element and put them, like you will be clearly understanding now. See here, place one pointer here and another pointer here. Okay. Now just check whether this one and this one, which is smaller, towards same value. So you can take any one of them. So I will take this value. Okay. Now just construct a node and put one. Okay. And make this to shift here. Right. Now whether one is small or two is small. One is small, right? So we want to put that. Okay, you may ask why we are going to put this one, because this one is smaller among this all linked list in root 1. Okay, and this 2 is smallest among this root 2. So this 1 is smaller than 2. That means this 1 is smaller among all of the other nodes, right? So that is the concept behind this merge sort linked list. Okay, so say, so here comes what? 1 again. Okay, now again move this one here. Now whether 3 is small or 2 is small, 2 is small, right? So put 2. Okay, come here, 3 and 3, so they are equal. So take any one of 3. So I am taking this 3. Okay, I took this 3. Fine. Then it goes to none. It goes to none, which means there is no element left here. So these all elements should be my answer, right? So just combine these all elements. That's it. So this is my output, right? So this is my second approach. What is my time complexity and space complexity for this approach? It is also time complexity of O of n plus m. Then space complexity of O of n plus m. You may ask, here also space complexity, here also space complexity, but what is the difference? Here we used an extra auxiliary array and a linked list, a new linked list. But here we used only the new linked list. Can you note the difference? It is slightly optimal. Okay. Now, what is the optimal solution? You have to know about this, right? What is the optimal solution? Then this is also not optimal. This is also not optimal. Then what is the optimal? Okay, let me take the node. Right. Now, first of all, I want to know that in linked list we can do an operation by using address, right? In array we don't have address. Okay, we are forced to construct a new array if this question is asked regarding the array. But in this question they clearly stated that it is linked list. So can we use this next, that is the next node addresses our any connection links, right? Just come up with me the same approach. If you understand this approach, it is slightly different. First of all, I am placing 2 pointers here. Now I'm going to check which is smaller. Okay, two are same, but now in this time I'm going to use a resultant variable. So my resultant variable will face what? Will face the first smallest node. Okay, now this is the first smallest node. Okay, my resulting pointer facing here. Now move pointer here. Okay, now which is the smallest element? Either one or two. One is the smallest element, right? So I will make a connection between them. Between them. Can you understand? Right? Now move this pointer here. Now again, what is the smallest node? Is 2. So I will take this one and connect here. And again, I will move this pointer here. Now what is the smallest node? It is itself. Okay. Now it moves here, which is equal to none. So I found none. Then it means all rest of the node will be answered. So I will connect here. That's it. I don't want to go. Just connect. Now see here. First it is 1, then 2, then 3, then 4, then 10. I got the answer, right? What is the time comes t? My time was is O of n plus m. And what is my space comes t? I can say it is O of 1. I didn't use any space. I just replace the next node address in the same linked list. So this is the optimal approach. Okay. Now let us see these two approaches. And I don't want to tell you these two approaches, this brute force and this better approach. But I want to show you the code for this optimal approach. Try these two approaches. If you don't know, feel free to comment. I will make the new video. Okay, but we want to see this optimal approach as our code. And then we are going for the recursion approach. I will tell you the recursion approach, then we can see the code. First, let us see this optimal approach here. If not L1, which implies there is no L1, then L2 is my answer, right? See here, instead of root 1, I replace as L1, and instead of root 2, I replace as L2. Okay, don't confuse. Now, if there is no L1, then L2 is obviously the answer, right? So return L2. If there is no L2, then return L1. That's it. Now, if L1 dot value is less than L2 dot value, then result will be what? Result will be L1. Understood? Now, result is equal to current is equal to L1. L1 is equal to L1 dot next, which means we are just initializing current and result as L1, and L1 is moving to next. That's what we have done, right? Now, else I will do that in L2. That's it. Now, while L1 and L2, while there is L1 and L2, they both are not equal to none, then I should proceed with my if L1 dot val is less than L2, then what should I do? Current dot next is equal to L1. It is not result dot next, it is current dot next. Why? Because we are keep on tracking with the nodes. Okay, see here. You may observe here. First it is 1, then this one, then 2, then 3, then 3, then 4, 10, like that. So wherever we want to connect, there we will make our current to move to the next node. Okay, fine. Now current dot next is equal to L1, and L1 is equal to L1 dot next. Else I have to do this for L2. Now if not L1, then it is what the case after finishing the loop. This loop terminates three possible ways. What are the possible ways? If L1 is none, or L2 is none, or both are none. Okay, possibly if L2 is there, then what should I do? And L1 is there, then what should I do? Like that. If not L1, then current dot next is equal to L2. Don't worry, if L2 is none, just current dot next is equal to none. That's it. Okay. If not L2, then current dot next is equal to L2. Then return the result. That's it. Can you understand this code, right? Let me submit it. It is submitted successfully. Now it's time to see about the recursion approach. In recursion approach, listen this carefully. It is quite similar to this previous approach. Okay, listen carefully. Now initially I am here and here. Okay, So in recursion, what is a recursion relation? Now we are going to write a recursion relation like first one is root 1 and second one is root 2. Okay, so this is going to be our recursion relation. Can you understand up to this? Right? Okay, we are going to pass two arguments inside the recursion. Now, this root 1 keeps on track of this linked list 1 and this root 2 keeps on track on this linked list 2. Okay. Now, if I give recursion of, take for example, node 1 address, comma, node 1 address, which means two pointers are facing like this. Okay. If I give recursion of node 1, comma, node 2, which means 1 is here. This root 1 is here and root 2 is pointing here. Can you understand this, right? So this is how the relation is going to be. Okay. Now, talking about the base case. What is our base case? When should we end? If there is no root 1, then it should return what? Root 2. If there is no root 1, then obviously the current root 2 will be my answer, right? If there is no root 2, then my current root 1 will be my answer, right? So this is going to be our base case. Okay, now it's time to go in for the body of the recursion. Now, just observe this carefully. Initially, they both are like this. Now, I'm going to check whether which is the smallest element. So I can say this is our two are equal. So I am going to take this one, this one. Okay. Now I will take this one and I will make this pointer move here. Like I will take this root. So I will take root 2 and dot next is equal to recursion of root 1 comma root I took, right? So root 2 dot next like this. So I'm going to do like this. Can you understand now? Right? Which means I took this root 2 node. Root 2 node I took. Now it's time to check for these all nodes, like from this 1 to this 10 and this 2 to this 3. Right? Then again I will take this 1. Now I will take root 1 dot next is equal to recursion of root 1 dot next comma root 2. Can I understand up to this, right? So this is going to be our body of the recursion. So what is our condition? If root 2 is smaller, then this is going to be executed. If root 1 is smaller, then this is going to be executed. Can you understand? If root 1 is smaller, I will take root 1 and I go for the root 1 dot next and root 2. If root 2 is smaller, then I am going to find the root 1 dot next. Sorry, root 1 is smaller than root 1 dot next and root 2. Right? Now let us move on to the recursion stack diagram. See here. Let us consider the same example. Like this is the example. Okay. Now initially here, what will be my root 1? It is 1. Okay. So root 1 is 1 and root 2 is 1. Okay. It is coming here. Whether root 1 is not root 1? No. So these two conditions are not executed. No. If root 1 dot val is less than root 2 dot val, no. Then else statement will be executed. So root 2 dot next is equal to self dot recursion of root 1 comma root 2 dot next. Okay. So root 1 is what? It is 1. Fine. So here also this root 2 will be 1 and next. Okay. Which is equal to, it is connected to this function, this recursion call. Okay. Now root 2 is what? Root 1 and root 2 initially here. Now its root 2 is what? 2. So 2. So it will be calling here. Okay. Now it is 1 and it is 2. Okay. These two conditions are not executed. Now if root 1 dot val is less than root 2 dot val, yes. So I will take this root 1, which means 1, and this next will be under the recursion call. Recursion call of what? Root 1 dot next. Okay. What is root 1 dot next? It is 3. Okay, 3, and it is 2. Okay. Now again going for the recursion call. Now let us go for this recursion call. Now what is our value? It is 3 and 2. So these two conditions are not executed. Now if root 1 dot val is less than root 2 dot val, no. So else part will be executed. So I will put this 2 and this next is linked with this recursion call. And what is root 1? Root 1 is 3. And what is root 2 dot next? It is also 3 in the linked list, right? Now, again, this will be calling here. Okay. Now, 3 and here also 3. This is also not, this is also not true. Now, whether the root 1 dot val is less than root 2 dot val, no, so I will go for the else condition. Now it is like 3 and this next is linked with this recursion call. Now what is my root 1? It is 3. And what is my root 1 2 dot next? It is none, right? It is none. Fine. Again this goes for the recursion call, but it is 3 comma none, right? It is 3 comma none. So I can say root 2 is none, so I will return root 1, right? So what is my root 1? It is 3. Like what is my root 1? 3. And then what are the value? 3, 4, 10, right? So 3, 4, 10 is my what? Root 1 value. So I will return here. If I return here, what is my linked list that is exiting in this return statement? This 3, 4, 10. So this 3 is connected to this 3, 3, 4, 10. Okay. So this will be returned. Return root 2, right? So root 2 will be returned. Okay. Come here. Here, what is my linked list? Let me change the color. So here, what is my linked list? It is 3, 3, 4, 10. Right? Again, it moves where? Above. So here, what is my linked list that is returned by this function? 2, 3, 3, 4, 10. So replace here 2, 3, 3, 4, 10. So this will be connected with what? This 1. So now this function will return what? This root 1. So it will return what? 1, 2, 3, 3, 4, 10. So 1, 2, 3, 3, 4, 10. And this will return what? Root 2. So what is root 2? 1, 1, 2, 3, 3, 4, 10. So this will be my output. That's it. So this is our recursion approach. Okay, coming to the time complexity and space complexity. What is the time complexity? I can say time complexity is O of n plus m at the worst case. Okay, and what is my space complexity? It is also O of n plus m. You may ask why it is, but it is called stack space. Okay, it is not an optimized solution, but why we are studying this? Because we are studying this for the extra approach. Okay, already I have told you 3 approaches. So this is what the 4th approach, this recursion approach. By this approach, you can know well about the recursion statement. Now, let us resume the code. Let me comment this. Fine. Now, coming to this code, if not root 1, what should I do? Return root 2. If not root 2, I should return root 1. Now, if root 1 dot val is less than root 2, means what should I do? Root 1 dot next is equal to just a recursion call to root 1 dot next comma root 2. That's what exactly written there, right? And then in else statement, it is ulta, just opposite, right? So let me submit it. Oh, root 2 1. Okay. Sorry, I just kept this as L1, right? So let me change it to root 1 and here also root 2. Yes. Now let me submit it. Yes, it is submitted successfully. Thank you.